Welcome to new physics class on units and measurements for class 11. As the chapter is a very vast one, we will make this video in some parts, and this is the first part of this chapter, units and measurement, chapter number 2 for class 11. You know, in physics, rather moreover in science, we require measurements. Without measurement, science cannot be learned. So for verification or prediction, we need measurement. So what is meant by this measurement? What is required or what are required for measurement? You know, measurement is nothing but this is a comparison of any physical quantity with a standard unit. That comparison of any physical quantity with a standard unit is called measurement. Suppose you are going to measure the length of a pen, then we require what? A measuring scale. Now by using that measuring scale, we need to measure the length of that given pen. Now if that scale has a graduation in centimeter or in millimeter or in inches, then as per your wish, that whether you are going to measure the length in terms of centimeter, in terms of millimeter, or whatever it may be, whatever that is graduated in that scale, okay, on that scale. Now just to measure that length, let's take it that the unit chosen is what? In centimeter. Suppose there in the scale you will find the marks 0, 1, 2, 3 centimeter, so on. So if you are going to measure the length of your pen and it comes out to be 10 centimeter, for example, then the length of that pen is what? 10 centimeter means what? That standard unit 1 centimeter is coming 10 times. That 10 times of that 1 centimeter is equal to the length of that pen. So that 1 centimeter is a standard unit for the comparison of that length of the pen with that 1 centimeter. How many times that 1 centimeter is coming in the measurement of length? So that standard unit, okay, that is a standard. Standard means constant. It will be same wherever it goes, okay, throughout the country, throughout the state, throughout the country, throughout the world. That 1 centimeter is conventionally accepted. So if we are going to measure anything, then we need a comparison. Comparison with what? With that standard quantity. And that standard quantity, the smallest one, we call it as a unit. Now next is what? Physical quantity. Physical quantity is what? All the quantities in terms of which laws of physics are described and whose measurement is necessary are called physical quantities. In a very simple and a short definition, you can say physical quantity means what? Any measurable quantity. Okay, any measurable quantity is known as what? Physical quantity. Suppose if you are going to measure the length, the mass, okay, the time, all these are measurable quantity. Mass means what? The amount of matter present in a body. If you are going to measure the amount of matter present in a body, then we need to measure it. So those measurable quantity, we call it as what? Physical quantity. Mass is a physical quantity, okay. Time, okay, the time duration between two events, we call it as time duration or simply time. That can be also measured. So time is also a measurable quantity. The speed of our mind, we can't measure it. We can't measure the speed of our mind. Suppose if you are thinking that you are in somewhere else, in Hawaii Island, for example, then immediately you may be there. Okay, so imagination. So your mind, the speed of your mind can't be measured. So your speed of your mind is what? Not a physical quantity. The beauty of a woman, okay, we cannot measure it. It depends upon person to person. It is subjective. We can't measure it. So those are what? Which are not measurable are known as what? As not physical quantity. Those measurable quantities are known as what? Physical quantities. Now units, as I have said, a definite amount of physical quantity is taken as the standard unit. This definite amount, okay, of that particular physical quantity is taken as a standard unit, and for defining this standard unit we will come later on. Okay, and this standard unit, as it is standard, it will be same throughout the world. Got it? Now the standard unit should be easily reproducible, and it should be also internationally accepted. That means all over the world, the scientists all over the world had accepted it, and that particular amount of physical quantity, that definite amount, will be used as a standard unit. Got it? Yes. Now as I said, physical quantity, again it's coming here, any measurable quantity. As I told you that any measurable quantity is known as what? Physical quantity. So this physical quantity in physics may be of two types. The first one is what? Physical quantity. Okay, the first one is what? Fundamental quantity. So you can say fundamental physical quantity. Next is what? Derived quantity or derived physical quantity. What is meant by this fundamental quantity and derived quantity? Fundamental quantity, okay, is the quantity which is independent of other physical quantity. If it is independent of any of the other fundamental quantity or any other of the physical quantity, then we call it that as fundamental quantity. Fundamental means basic. Okay, so that of length, for example, mass, time, okay, these are all what? Fundamental quantity. Length and mass, okay, cannot be related. While we try to measure the length, mass cannot be interfere with the measurement of length, like that. Likewise time also. So they are all independent of one another. So such type of the physical quantity which are very basic and which are independent of one another, we call it them as what? Fundamental quantity. Now what is meant by derived quantity? It is a physical quantity which depends upon other physical quantities that are known as what? Derived quantity. Derived quantity means this quantity is derived from what? Fundamental quantities. In deriving that quantity, what we call as derived quantity, we may require what? One or more fundamental quantity. Then that type of physical quantity, we will term it them as what? Derived quantity. For example, let's take it from the simplest one, area. Area is equal to what? The formula. It may be length into length, or it may be of length into breadth. While we try to find that length into length, that length, another length, length into breadth, for example, in the case of rectangle, so we require that length 2 times to measure that length as well as breadth. So this area is derived physical quantity. Why? Because we require this length. Okay, now in the case of speed, distance divided by time, we call it that as what? Speed. So distance is also what? Length. time is also one of the fundamental quantity, so we require two fundamental quantity to derive this speed. Likewise, velocity same. Velocity means what? Speed with direction. We call it what? Velocity. So it may be what? Acceleration, displacement, whatever it is. If it require more than one or more fundamental quantity to express a given physical quantity, then that physical quantity we call it as derived quantity. Those units which are used to express fundamental quantity we call it as fundamental unit. For length it will be expressed in terms of meter in SI unit. Okay, in terms of mass it will be kg. In terms of for time, the unit SI unit will be what? In second. So this meter, kg, second to represent or to give this fundamental quantity in terms of that unit, we call it that as what? Fundamental unit. So fundamental unit of length is what? Meter in SI unit. Fundamental unit in SI unit for this mass will be in kg. Likewise, similarly second, like that. So there will be 7 fundamental quantities. Okay, we will come later on after this. Now let's go to the derived one. But in the case of derived physical quantity, there are numerous numbers of derived physical quantities are there, and those unit to express this physical what derived physical quantity, we call it them as derived units. For example, for the derived physical quantity like that of speed, it will be meter per second. For area, it will be meter square. For velocity, the SI unit for this derived unit will be, for this derived physical quantity will be what? Meter per second. Speed and velocity will have same unit. Now this is about your SI unit, as I have told you, but in the case of unit it may not be what? SI unit or system of international D unit. Okay, it may be in other unit also, but this SI unit will be used in our standard, okay, in our prescribed book, okay, and we will have to use this for our future discussion in the class. Now this is CGS unit. CGS means length is measured in centimeter, mass is measured in terms of gram, and time in terms of second. Feet poundal system, we call it FPS. Length is measured in terms of foot. Weight or mass, not weight, mass will be measured in terms of pound, and time in terms of second. This is MKS system, and it is equivalent to that of this SI unit. Length will be measured in terms of meter, mass in kg, and time in second. So it is the standard scheme of weight and measures. Okay, these are the standard system, but out of this we will use what? This SI unit or MKS system. Got it? There are 7 base units, as I said. Okay, fundamental units. These 7 base unit we also call it as 7 fundamental units to represent what? That of what? Length, mass, time, temperature, amount of substance, electrical current, and luminous intensity. Now what is this fundamental unit? I told you about the fundamental physical quantity, okay, which are independent to each other. Just to represent those physical quantities, we need what? For measurement we require what? Fundamental units. Those physical quantities which are independent to each other are called fundamental quantities, okay, and their units are called fundamental units. Now as I told you that there are 7 fundamental units or quantity. Fundamental quantities are what? Mass. It may start from the length also, okay. In some textbook length may be given first. You can change the order, no doubt. So mass, length, time, temperature, amount of substance, electric current, luminous intensity, these are the fundamental 7 fundamental physical quantity in what? In physics, okay. So these are the 7 fundamental quantities, and these are their units. The fundamental unit in SI system, it will be for mass, it will be kg, length meter, in for time it will be in second, and the temperature will be measured in Kelvin, amount of substance will be measured in terms of mole, electric current will be measured in terms of ampere, luminous intensity in terms of candela. And these, their symbol to be used, it is also written on this right hand side. For kg, for kilogram it will be used as kg, for meter it will be represented by small m, for second it will be represented by small s. Okay, in some book you may find as sec for second, but you better write only single s. Okay, there is some square like structure here, but you should not write that one as square. Okay, it should be only s. And for Kelvin you have to represent by capital K. For mole, okay, amount of substance, mole, you have to write only mol, mole. For ampere, capital A, and for candela it will be CD. Small distance we can measure it by using measuring tape or scale. Okay, but for large distance, how we have to measure it? Like that of measurement of stars, the measurement of distance of stars, I mean. So the apparent okay, distance that we see about the heavenly bodies, like that of a star or a moon or that of a planet, how to measure these very long distances? We can't use our measuring scale or measuring tape to measure the distance of the moon from the earth, right? So we need to use some indirect method, and one of the indirect method that is used to measure these large distances is by means of parallax method. So first, what is parallax method? We need to know it. The parallax method is nothing but, suppose if you try to hold a pen in front of you, and if you close one of your eye, okay, and if you watch only through one of your eye, then that tip of the pen will be having its point on the background, say for example on the wall, on the wall. But if you change the position of your eye, that means by closing another, okay, by closing your eye and opening on the other eye, and if you watch it, then the position of the tip will be shifting onto the background, okay, onto the background of the wall. So that relative, okay, displacement or apparent displacement, you can say apparent displacement, or the shifting in the position of a stationary object with respect to the background relative to each other as viewed by an observer due to the change in the observed position is called parallax. That means the shifting of the positions of an object with respect to the background in relation to the change in the position of the observer is called as what? Parallax. Now suppose if we are trying to measure the distance or the length of the stars from our sun, then what happened? Let's take it that this is, let me little bit zoom in, okay, so that you will see it. Now let's take it that this is the position of the star, and this is our sun, this is our earth. So earth will revolve around the sun like this, okay, in this way. So what happened? This is in the case of January, we are taking in the diametrically opposite, okay, opposite sides on each orbit of the earth. When earth revolves like this, this is January, okay, and somewhere here it will be February, March, April, May, then it will come to June, like that. Got it? June, here July, August, September, October, November, and then December, then it will come to January, like that again. Got it? So you take it, just you make it that the sun is at the center, and you try to take it at the diametrically opposite position of these two stars, like this. Got it? And what happened if you try to observe the position of a particular star at this January, let's take it as 1st January, okay, for the sake of simplicity. On this 1st January day, you observe a star here like this, okay, by means of a telescope. Then this position will be the position of your telescope. Clear? And we are going to measure the angle, we are going to measure the distance between the earth and the star. Let that distance between the earth and the star, rather the distance of the star from the earth, let it be denoted by capital D. Now if you try to observe again when it is at the diametrically opposite of its orbit, then this will be the position of the line of sight, you can say. Line of sight, or you can say, if you are trying to use that of your telescope, then the telescope would have been here like this, at this position, okay, in this direction. So this will be the line of sight if you are observing from this position. Now you need to wait it till it comes to the 1st June. That means when it is coming here at the 1st June, then your position of the earth will be here when you go round here like this, okay, on its orbit. Got it? So from here again, on this 1st June, if you try to observe that telescope again, then that telescope position will be here like this. Am I right? And this will be your line of sight. Got it? Now what happened? There will be an angle subtending between these two line of sight, one along this, another along this. So this angle we call it as parallactic angle, or rather you can say parallax angle, but we call it this theta as parallactic angle. And the distance between the two points or position of the observer, one here, another here, and this distance we call it as basis. So your D is known as what? Basis. And we call it this theta as what? Parallactic angle, right? Parallactic angle. But if we know this D, okay, if we know this D and if we know this theta, then this distance between the star and the earth, which is denoted by capital D, can be easily found out. How? Let's see. Now see, this is the blue line is the orbit, okay, and how to find it out, that capital D. Now you know that in the case of an arc like this is the arc length denoted by S, okay, and this is the center of that circle. If you try to complete it, then it will be coming like this, right? And this will represent your radius. So the angle subtended by this arc length, okay, by this arc length at the center of the arc, this angle, if it is denoted by theta, then there is a relation between this S, R and theta, right? What is the relation between these two arc length, between these three? S is equal to what? The radius times the angle subtended by the arc at the center. So S is equal to what? R theta. Now in our case also, you take it this position of the star as the center of the arc, and you take it this arc length, okay, as this angle is very small. Your star is not very close to the earth, okay, this is very far away. So this angle theta will be very small, and if that theta is very small, then what happened? This arc length will be approximately equal to the distance between the two positions, or rather the diametrically opposite distance, which is denoted by small d. So your arc length will be equal to what? Small d. Am I right? and the radius here, instead of this small r, it will be represented by the capital D. So your arc length, that is equal to D, this D will be equal to what? D means what here? The arc length. Okay, and theta will be equal to theta, no doubt, instead of r, which is equal to the arm of this angle theta, that is nothing but for us it is here the distance between the star and our earth, that is denoted by D. So D will be, small d will be equal to capital D into what? Theta. Am I right? So if you know this, what, theta and small d, then you can easily find out capital D. How? Your capital D can be easily found out by what? Your capital D can be expressed as small d divided by theta, right? So if you know the distance between these two diametrically opposite sides of the Earth's orbit, which will be equal to the what? Major axis of the elliptical orbit. If you know this D, which we call it as basis, and if you know this parallactic angle, then you can easily find out this distance between the Earth and the star. Got it? But the question is, how we will find this parallactic angle theta? Now that one I will tell you, okay? Now look, suppose at this position, when you are looking through the telescope, okay, your line of sight, that means line of your vision, is along this. Am I right? So you try to keep this line of sight here like this at one position, and that means this line of sight, first line of sight, while you are watching when the season, when the date is 1st January, so this is the direction. And by observing or by tilting the direction of the telescope when it was viewed on the date of this 1st January, the line of sight, you try to draw another parallel line parallel to what? Parallel to this line of sight at this 1st June. So if you know these two angle, okay, then you can easily know this one. Am I right? Why? Because this is the line of sight on that 1st January, which will be equal to this, right? And the line of sight at the second observation, that is on 1 June or 1st June, that will be in this direction. So this angle, it will be also equal to theta. Why? Because this is also equal to the parallactic angle theta here, because these are two vertically opposite angles. So if you know this angle theta, then you can easily find out this parallactic angle. So likewise, if you know this parallactic angle, then what happen? Your capital D can be expressed as distance between the two diagrammatically opposite, okay, positions of the Earth, which is equal to small d. We call it this as basis. And if you know this parallactic angle, then you can easily find out what the distance between the sun and the Earth. Likewise, also you can measure the diameter of heavenly objects, like that of a moon, in the same way. Okay, that one, whether it is here or not in the slide, let me see. But if it is there also, yes, it may be there. Let me tell you when it comes. Okay, now see here, measuring large distance, whatever that I have talked to you, it will be all here. Okay, so parallax is a displacement or difference in the apparent position of the object viewed along two different lines of sight. Okay, you can give this as a parallax. Okay, definition of parallax also. So parallax is a displacement or difference in the apparent position of an object viewed along two different lines of sight. Okay, when it was at the 1st January and when is again in the first zone. So the angle between these two line of sight, we call it as what? Parallax, right? And is measured by the angle of inclination between these two lines. Okay, the distance between the two viewpoint is called basis. That means when the Earth was at 1st January, at the 1st June, the distance between the two positions of the Earth, where we take it as the two positions of the observation, okay, one at 1st January, another at 1st June, the distance between them we call it as basis. In that example of that one pointing a pen in front of you, okay, if you try to close one eye, you will see the tip of the positions on the background on the wall at one position, and when you open another what eye by closing the previous one, you will see the position of the tip on the wall will be what at different positions. So the distance between, in this case, okay, in this example, the distance between of your eye will be nothing but that will be the basis. Okay, in our case, the positions of the 2 points of observations of our Earth, that is at 1st January and 1st June, that distance, rather, that will be your measure axis of your Earth orbit, as I told you, that will be the basis, and it is denoted by B. Got it? So that can be, this can be also given as an definition. And for measuring of a planet using a parallax method, that means measuring of a distance by parallax method, as I told you, that one, okay, here it is also given, right? Now suppose if you are going, this is almost the same as we have discussed in the previous case. Your theta will be equal to what? D by capital D. This theta will be known as angular size of the planet. Okay, suppose if your planet is like this, suppose this is your planet, for example, and you are observing from the Earth here, okay, and if you try to observe the planet on one of its edge like this, and from that same point of observation, if you try to observe on another opposite edges of the planet, then this angle, we call it this angle as theta. Okay, and this diametrically opposite, okay, side, this will be termed as what? Your D. And this D will be nothing but this will be the diameter of that planet. So if you know the diameter of the planet, then you can easily find out the size of that planet. And capital D is nothing but this is the distance between that planet, okay, and that of the Earth here. Your Earth is your observation, point of observation. Okay, so likewise you can find it out, this angular size theta, okay, and at the same time, if you know the distance between this Earth and the planet D, you can also find out the distance, the diameter, or rather the size of the planet. Got it? Yes. Yes, it is also given here, the same thing. Okay, as I told you that this, if you take it that this is the basis, that we take it, just I am just inverting it, okay, the previous diagram. Okay, this will be the point of observation, this will be the size of the planet, which will be denoted by small d, which will be denoted by small d. This distance capital D will be their distance between the sun, between the Earth, your point of observation, and the planet. You have to assume that this is no more your Earth, okay, rather you have to take it that this is a huge planet. Okay, this, it may not be seen like this as a huge, but I'm just drawing in a very magnified way. Okay, so by knowing what your theta and the distance between the Earth and the planet, you can easily find out the diameter of that planet, rather it will give you the size of the planet. Got it? Yes, let's see. Suppose if you take it that this is the planet, the blue one, okay, the edges the 2 point of edges, if you observe by using your telescope, if you try to observe it here from here like this, okay, this will be the line of sight for that one of the edges of the planet, and opposite to it the edges somewhere here. If you observe it, then your telescope will be also here like this, so that your line of sight will be along this. So if you know these two angle, the angle between the two line of sight, that is theta, this may be called as parallactic angle in the previous slide, okay, at the time of measurement of the distance between the earth and the planet, or earth and the star. Got it? In the same way, the same formula can be used to find out the size of the planet like this. Got it? Yes. Now let's go to what is meant by significant figures. Now for every measurement there will be always two terms, one which is very much accurate, okay, one part which we think that is very much accurate, and there is some small part which is very much uncertain. We can't say that definitely up to this point it is exactly correct, okay. So there is some uncertainty part, that we call it as some error, okay. That part which we can say certainly that up to this it is exact, or up to this the measurement is correct. Suppose in that example of measurement of length, I told you that it is of 10 centimeter, but who knows, in that measurement, suppose if it's not exactly at 10 centimeter, it is little bit more than 10 centimeter, but it is again less than 10.1, okay, 10.1 centimeter. That means in between 10 centimeter and 10 plus 1 millimeter, 10.1, okay. So your length of the pen lies between 10 centimeter and that of 10.1. Got it? If it is exactly at 10 centimeter, it is okay. But if it is not exactly at 10 centimeter, but it is little bit more than 10 centimeter and less than 10.1 centimeter, there lies some uncertainty. We know that it is little bit more than 10, so up to 10 it is very much certain. Yes, the length is accurate up to 10, but we can't say that whether it is how much it is more than that 10 centimeter, whether it is 10.2, 1, or whether it is what 10 point what no I'm sorry that 10.01 or 10.03. But this 10.01, 03, 04, 05, 06, these are all less than 10.1 centimeter, okay. So up to that 10.1 centimeter, it is very much accurate. As I said, suppose I will draw the scale here, okay. This is up to 10 centimeter, and these are marked with 1 millimeter like that. 1, 2, 3, 4, 5, 6, 7, 8, 9. This will be 11. So this will be 0.5, okay. Suppose if you are going to measure that scale, the length of the scale is somewhere here like this, or rather the pen, okay. If you are trying to measure it from 0, this is not in terms of the scale, okay. Now you take it this as 0 and this as 10, for example. So this up to this 10 it is okay, but here it is 10.1 is here. So your pen lies between 10 and 10.1. Got it? So up to 10 we know that it is very much accurate, but we can't say this remaining part. Got it? So we may write that 10 as 10.01, something like this, or it may be 10.02, 10.03 like this, so on up to 10.09. So your 10 is what? The certain part which is very much reliable, and this part, the remaining part, which is not reliable or it is uncertain. So every measurement will incorporate with this error, Okay, the uncertainty part, we call it that as error. Due to this uncertainty, error comes up. So while we are trying to measure it for any of this physical quantity, then we need to report it. Okay, how much the length is coming, how much the mass is coming, we need to note down it. That noting down, we call it as reporting. Got it? So while reporting what happened, there will be a certain figure, what we call as what significant figures. So what is these significant figures? Significant figures are nothing but these are the figures which are what, those digits which are very much certain plus one more digit which is uncertain. Okay, the combination of these digit of the certain, okay, digits and that of one uncertain digit, collectively we call it that as significant figures. Okay, here you will find in the definition also, the significant figures are normally those digits in a measured quantity which are non-reliable. Non-reliable means non-correct, plus one additional digit that is uncertain. In that my example, it was 10.01 or it may be 10.02. We will not take it that 0.01 together. Okay, we will have to take only one digit from that uncertain part. So the certain number of digits in that certain, in that measurement which is very much certain, plus one digit from the uncertain part, collectively it will give you what is known as significant figures. Got it? So there are some rules for what measuring of these or counting of these significant figures. So what are those rules? Let's see. All non-zero digits are significant figures. All non-zero digit means those number which doesn't have any zero. For example, that of suppose 2, 3, 4, 5. Okay, 2345. So these doesn't have any zero in each digit. So what happened, we will say that this number 2345 has four significant figures. Got it? In that way. Now next, let's go to the another one. All zeros between two non-zero digits are significant, no matter where the decimal point is, if at all. That means all zeros which are between two non-zero digits. Okay, for example, you can see here 40056. There are two zeros here in between two non-zero digits. 4 is non-zero, 5 is non-zero. Okay, this one 40,056. So in this number, what happened? There are two zeros in between two non-zero digits. So this number will have five significant figures. Similarly, if you are going to have that decimal, okay, number 209.08. Got it? So 209.08. Here 10 is here in between two non-zero digit. Another 0 is also here between two non-zero digits. So we have to take into account all these zeros which lie between any two non-zero digits. So how many digits are here? 3, 4, 5. So this also has what? 5 significant figures. So both these numbers have what? 5 significant figures. Next, all zeros to the right of the last non-zero digit are not significant, but such zero are significant if they come from an actual measurement. Got it? For example, this 56060, the zero there in the right side of this what? Last non-zero digit 6. Okay, this will not be significant if it is given here as a number, but if it is coming from the actual measurement, then we have to take into account this 0 as also a significant figures. Otherwise, this number will have only 4 significant figures. Suppose if this is coming from the actual measurement, say for example in terms of 56060 centimeter, 56,060 centimeter, then there this 0 is also significant in that case. Got it? If it is actual just a simple number like this, then this 0 will not be significant, and this 56,060 will have only 4 significant figures: 5, 1, 2, 3, 4. So 4 significant figures like that. Okay. Yes, next number. If the number is less than 1, okay, that means if the number is less than 1, it will be 0 point something like that, right? All zeros to the right of a decimal point and left of the non-zero digit are not significant. In my typing here, some mistake is there. You need to say like this: all zeros to the right of a decimal point. Of A is repeated. Okay, you remove one OA. Okay, you take it out, this OA. So all zeros to the right of a decimal point. Right of a decimal point means from that decimal point you need to take toward the right side. Okay, like this. From a decimal point you need to take the right side like this. So 0.034, these two zeros are on the right side of the 0, and left of non-zero digit are not significant. So these two zeros which are on the right of decimal point and left of non-zero digit, these 0 are not significant. So your 0.0034 has only what? 2 significant figures for these 3 and 4. 1 digit, 2 digit, so it will have 2 significant figures. Got it? Yes. Next, all zeros to the right of a decimal point and to the right of a non-zero digit are significant. For example, your 0.12340. Okay, this 0 is to the right of a decimal point. Okay, from this decimal point 0 is right, and also the right of this non-zero what? Digit. So what happened? This will be a significant figures. So how many significant figures are here in this 0.12340? It will have 5 significant figures. 1, 2, 3, 4. 4 digits. You need to include this 0. Why? This 0 is onto the right side of a decimal point as well as 0 of the non-zero digit. So this will have 5 significant figures. Next, now single 0 conventionally placed to the left of the decimal point is not significant. While writing, we never write it as 0.12340 like that. Okay, we generally place 1 0, okay, conventionally onto the left of a decimal point. So that 0 is what? Insignificant. Got it? We need not to count as a significant figures for such 0. Got it? And the last one, this is also very important. The number of significant figure does not depend on the system of units chosen. Okay, whether it is measured in terms of centimeter or in terms of meter, in terms of kilometer, the significant figures remain unchanged. For example, I have given you one example, 14.5 centimeter here. This 14.5 centimeter can be expressed as 0.145 meter. 14.5 has 3 significant figures. Same thing, 0.145 meter is having also 3 significant figures. Or if you want to express in the form of standard 1, then it will be 14.5 into 10 to the power minus 2 meter. So this also has what? 3 significant figures. This 10 to the power something we will not take into account in terms of significant figures. Okay, we need to take it only these base only, 14.5. So how many digits? 3. So what happened? This 14.5 centimeter, 0.145 meter, or 14.5 into 10 to the power minus 2 meter, all these will have what? 3 significant figures. Okay, if you want to look it, then I will zoom it here like this. So 14.5, 0.15 meter, 14.5 into 10 to the power minus 2 meter, all these will have what? 3 significant figures. Okay, now let's go to the addition and subtraction with significant figures. Okay, if you are going to add two digits, okay, then how will you express the sum? Okay, or if you are going to take a difference of two numbers, what will be the significant figure in the difference? Rather, in the case of multiplication and division also, how will you express the product, how will you express the quotient? Okay, that one is going to be discussed here. Suppose if you are going to add or subtract two numbers which are not having the same significant figures, then the result, rather your what sum or difference or product or quotient should be expressed in terms of that significant figure which has minimum significant figure. For example, here in the case of, let's take it, two numbers a and b which has what three four significant figures, 334.5, this has four significant figures, and 23.4, this number has, B has what, three significant figures, A has four significant figures. So when you add it up, it comes out to be 334.5. Okay, now what happened? This 334.5 plus 223.4, if you add it up, then it comes out to be 357.9, right? But this one is having four significant figure, B is having three significant figures, so the sum must be also what, expressed in terms of that minimum significant figure. So minimum of these two is what, 3, so you need to express the sum, okay, which will have only three significant figures. So you need not to express this 9, so you need to have that what, correction, rounding off, we can say that one, as this 9 is more than 5, so you need to add 1 here, so that it will be what, 358. That is what it is expressed here. Same is the case in the case of difference. Okay, in the case of sum also, in the case of difference also, in the case of product, in the case of division also, you need to express like this in terms of the least what, significant figures. Got it? Let's try to solve some of the numerical problems so as to apply whatever we have learned. Okay, so this is problem number 2.16. Find the significant figures in the following. The first is 0.007 meters square, and we know that the decimal point after that, onto the right of the decimal place, the zero that is coming, these are not significant. The zeros, all zeros coming at the right of the decimal point are not significant, so this will have only one significant figure. The second one is 2.64 into 10 to the power 24 kg. So all that is coming in the scientific form, that is 10 to the power of 24, this will be insignificant. And 2.64, this will have only three significant figures. It is also given here. The next one is 0.2370. Now in this 2.370, here the decimal point that is coming after the non-zero quantity, as it is less than 1, all this zero that is coming, okay, the zero is coming after this non-zero quantity after the decimal point, this will be significant. So all these numbers will be of significant figures. That means 1, 2, 3, 4 significant figures. Likewise 6.320, the number E, this one, and number D, 6.320, this will have what, 4 significant figures, because this is a number which is greater than 1 and 1. So what happened, this will be of the 0 that is coming after the decimal point and right of a non-zero digit. This will be what having what significant. So this 0 is significant, so it will have 1 2 3 4 4 significant figures. This one is less than 1, but this one is greater than 1. So for less than 1, that means 0.2370, all the 0 that are coming after the decimal and onto the right of a non-zero digit, that will be what significant. But here in this also, as this is also a number which is greater than 1 and all those zeros coming after the decimal point and to the left of a non-zero digit will be what significant. So this 6.320 is having 4 significant figures. Now what about the number E, 0.00636032? Now as it is set in this first one, all those zeros after the decimal point, that means the zeros, all zeros coming to the right of decimal point and left of a non-zero digit, this will be, these 3 zeros will be insignificant, so it will have 1 2 3 4 4 significant figures. Similarly, like that 6.032, as this 0 is coming in between two non-zero digits, so all these digits will be significant figures. So 1 2 3 4, this will have 4 significant figures, right? Let's see about the next questions. And this is for the problem of what addition of numbers and what should be assigned in the sum or a difference or in the product. And we have learned in the theory part that when when two or more numbers are added or subtracted or multiplied or divided, then the result will be expressed in the minimum significant figures of all those numbers. Now here in the problem number 1.7, the length, breadth and thickness of a metal sheet are 4.234 meter, 1.005 meter and 2.01 centimeter respectively. Give the area and the volume of the sheet, okay, to correct significant figures. So length, breadth and thickness are given, and these length and breadth are of having 4 significant figure each, but thickness is having only what 3 significant figures. Mind you that this length and breadth are given in meter and thickness is given in centimeter, so you need to convert it in terms of meter so as to have the same unit, okay, length, breadth, thickness in terms of meter. Now when you convert this centimeter into meter, it will be 2.01 divided by 100, just to convert into meter, okay, divided by 100. 100 in the denominator is equal to 10 inverse square, okay. So what happened, this thickness has 3 significant figures, others are having length and breadth are having 4 and thickness is having what 3 significant figures. So whenever there is the factor of thickness, the result should be expressed in this minimum 3 significant figures because others are having 4 significant figures. Now in the finding of area of the metal, length into breadth, so length into breadth means what 4.234, which is also having 4 what significant figures, and the breadth is also having 4 significant figures. When you multiply it, you need to express it in 4 significant figures. So this is what 1 2 3 4 5 6, so this is having what 6 significant figures. So you need to round off and you have to give only 4 significant figures, okay. So this one 1 2 3 4, so you need to express up to here, that means it will be 4.255 meters square. Got it? And for a volume, we need to find out the length, breadth and thickness. Length, breadth are having 4 significant figures each, whereas thickness is having only 3 significant figures. So the product is coming out in this way: 8.55289 into 10 to the power minus 2. You try to multiply it and you just check it whether you are getting like this or not. Now see what happened. This is having how many significant figures? 6 significant figures. 1 2 3 4 5 6, right? 6 significant figures, but we need to express in the minimum significant figures. Okay, the least significant figures out of this factor is what? 3. So we need to express that least significant figures in the product. Okay, so after rounding off, volume is given. Okay, it gives 3 significant figures. That is what? Volume is equal to 8.55 into 10 to the power minus 2 meter cube. So there must be a unit coming there, meter cube, as meter cube. So this will be having what? Meter cube, right? Like that. That unit is missing. So with this we will try to come to the end of our today's class, and the other remaining parts like that of what your dimensional analysis, okay, and that of errors, okay, combination of errors, we will try to cover it in the next video. Okay.